Okay, then. Welcome everybody to the fifth and final week of Cats for AI. I'm going to be telling you about monads today, which maybe you know a little bit about, maybe you've heard about, but I'm going to try to dispel some possible confusion here. So, first of all, the structure of the talk is that I'm kind of going to a little bit interleave examples and definitions, and this was to try to solve the problem of defining things in a way that is really hard to follow right at the beginning. But then the problem is I may end up talking about things and you won't know what I'm talking about. So please just feel free to ask questions. I'm kind of hoping to get a bit of feedback as we go about sort of how this stuff is appearing. So just jumping into it, the basic idea to get us started is that you can understand a lot about what a program is doing just by looking at how it manipulates types, right? What are the types of sort of each function, what's going into it, what's coming out of it. But this is really problematic with neural networks because every single type is basically a number. I mean, a bunch of numbers, but the sort of amount of information that's obvious in the typing of a neural network is really minimal. And so you might see a diagram like this. This is supposed to be a diagram for an lstM. And how are you supposed to interpret what's really happening here structurally speaking that makes it non-trivial? And to sort of start to reason about this thing, we've found it useful to bring in the idea of monads. And these are particular kinds of type constructors, and we'll get into some examples. Like, I guarantee you there's at least one or two monads that you're already very comfortable with. And we've sort of found this to be a good way to kind of abstractly capture what's happening in a computation. And one way that's important is to kind of align it with something classical. If you want the network to be able to perform some classical function, then it's good to know what structure exactly it should kind of have in common. And I'll say monads, like they're a really kind of core concept in category theory, and that means there's really a lot to say. I mean, you can really talk about them and just keep talking and talking and talking and talking and talking. And there's a lot there, so I'm not going to try to say everything that there is. I'm going to try to keep it scoped, but just don't expect to be 100% comfortable. We'll try to get close, but I just wanted to start with that note. And then before we jump into it, just some remarks on notation. So when I say a type, for this talk, I'm thinking of that as a set. So a type is just the set of instances of that type. That's not all there is to types, but this is good enough for our purposes at the moment. And I wanted to emphasize most of what I'm going to say, a lot of what I'm going to say is valid for arbitrary categories. Some of it's valid for arbitrary monoidal categories. Some of it's valid for arbitrary monoidal closed categories. If you're not sure what category I'm in, or you're not comfortable working in a general category, just assume I'm working in set with Cartesian product. That will be enough for the majority of my examples. And I don't think this notation was used in the course. I'm not sure, but I'm going to be using this bracket notation for the internal HOM. If you don't know what internal HOM means, I just sort of mean the set of all the arrows from A to B. So this is the same as B to the A, basically, the exponential object. Okay, so we're going to begin with the most fundamental monad that there is, because again, we want to start with some examples. So the most fundamental monad that there is the list monad. So everybody who's done any programming has spent a lot of time with lists, I believe. And list is just one basic way of taking a type and making a new type, which is the type of lists drawn from elements of that type. So if you have integers, then you have lists of integers. If you have characters, then you have lists of characters, and so on. But there's a little more than just making a new type, which is that also the elements can be turned into lists. So given an x, I can make a list x by just turning it into a one element list, right? So we identify the elements of x, the instances of x, with instances of lists that just have one element. And I also have a notion of concatenation. So I've written the listification or whatever here, this as eta, and this mu, this is concatenation. So if I have a list of lists, then there's a natural way of interpreting that as a list. And we can express this as a somewhat complicated commutative diagram. Actually, that's the next slide. Right. So the nice properties that these have, and these should all make sense to you. If I have a list and then I wrap each element into a list and then I concatenate, I get the original list back. Or I could wrap the outer list and then concatenate. That also gives back the original list. And that means we have some sort of compatibility there. And somewhat more complicated, if I have a list of lists, there's a priori two different ways of concatenating a list of lists. I can either concatenate the outer pair and then the inner pair, or I can concatenate the inner pair and then the outer pair, but we believe these should give the same result. So I've expressed this as a slightly complicated commutative diagram here, two commutative diagrams. So basically this says no matter how I follow the arrows in any of these diagrams, I get the same answer. Yeah, so I'm just going to leave this up for a second to soak in, because again, this expresses something that should be intuitive to you about lists. It maybe is just in a non-intuitive way. So, again, this is about saying there's two ways to concatenate lists of lists, and they're the same. There's also two ways of turning a list into a list of lists and then back, and they're the same and equal to the identity. Question, is this definition of list meaningfully different from the definition with a single element concatenation morphism? I'm not sure exactly what that definition is off the top of my head, but I think the next bit may clear that up. So okay, so this next question, Dobrik, we may answer that in the next slide. So the problem with computing using this list sort of type, this list makes new types, but very often you don't want to return a list. If you have some big program, maybe you have a number in, you have a number out. In the middle, you do something with lists. But how do you ever stop using lists, right? Once you've wrapped things up into lists, how do you escape? Well, you need some way to fold a list, which means that you need a type equipped with such a map that can smush lists down together into single values. Lists themselves do this with concatenation, but maybe you want something more interesting, which I'm going to call a model for list semantics. So, I mean, as a basic thing, you might look for the maximum value in your list and return that as a number, right? So what kind of properties should such a nice model have? Well, if we wrap something into a list and then fold it, we should get the same thing back. That seems sensible. And then also, if we, again, it's similar to before, if we have a list of m's, then we can either concat and then fold, or we can fold and then concat, and seems logical. Those should give the same answer if we want this to be kind of well-behaved and not too dependent on how the list is presented and so on. So again, we have kind of these commutative diagrams that we want to be the case for such a list interpreter M. Now, does anybody know what such an M is? That is, like, does anybody know another word for these M's that satisfy these conditions. Yes, monoid. List algebra is technically correct. But yeah, the conditions I just gave, they don't look at all like the axioms for monoids, but in fact, they're equivalent to the axioms for monoids. So what is a monoid? It's a binary and associative operation with a unit element. The binary operation, you get that from folding a 2-item list, and the unit element, you get that from folding a 0-item list. I think this is kind of an interesting example because my experience has been that a lot of programmers don't know the term monoid, but most of them know a lot of interesting monoids because they're constantly folding lists. So, one example would be, return true if one Boolean in this list is true, otherwise return false, right? That corresponds to a 2-element monoid, folding with a 2-element monoid, addition, maximum, and so on. So chances are something that you're using to fold lists is a monoid. It is a list algebra. So I wanted to point out this sort of nice fact about list algebras. So I'm using alglist to say, again, these list algebras, which we know are monoids. And we have this U, which is a forgetful functor. So what U does is it throws away the structure, and it just gives you back the set of instances. And then we have, again, lists. So I mentioned briefly that given any set, the lists of that set are themselves a list algebra under concatenation. So that is to say, you can always fold a list by thinking of everything in it as a list and then concatenating all of them. It's maybe not as interesting as you'd like, but you can always do it. So there's this list functor going into algebras for list, and then this forgetful functor that forgets the algebra structure. And one nice property that I would encourage you to verify is the statement that for any set X and any monoid M, we have this relationship that mapping X into the set underlying M is the same as sort of structure preserving maps of monoids from the lists on X into M. So what does this mean? It means that if on the right side, if I want to know where a list goes, then I only need to know where sort of the 1-element lists go. And then everything else is forced by the fact that I said it has to be structure preserving. It has to send the concatenation to the monoid operation, the whatever you want to call that, multiplication or something. And this kind of key property, this is sort of the notion of adjoint functors. This is gonna come up a lot. So basically, maps out of list are the same as maps into U. And I'm going to give this definition here, and don't worry, because somehow you mostly only need to pay attention to the left side. So an adjoint pair, we say F is left adjoint to G, means that we have 2 functors, F from C to D, G from D to C. These are any categories. And they have to satisfy this condition I just said, which is that maps out of F should be the same as maps into G. There should be a bijection between the two. Now, I've organized a few of my slides this way, which is this thing on the left. This is what you should take away. This is what you should have in your head. This should be the picture that that you kind of base your understanding on. But this orange bit, this is the annoying homework part where you have to go later and check all this stuff. So you should sort of think in these terms on the left. But in order for it to work, in order for the ideas to work as advertised, you need to check this thing on the right. So So here, what is this thing on the right saying? It's saying that this psi, this bijection between these two sets of arrows, it has to be natural. And what natural here means is anytime we have a morphism x to x prime, it has to behave in a predictable way. And anytime we have a morphism y to y prime, it has to behave in a predictable way. So this is the simplest definition I know of adjoint functors. But I think, again, thinking of it as maps out of F is the same as maps into G. That will get you most of the way there. Okay. So I think moving on to the second example, slightly different flavor, but you'll see a lot of similarities, is the maybe monad. So by maybe X, all that I mean is this is the type which might be an element of X, or it might be a null value, or sort of a failure value. So usually you don't see maybe used explicitly, but you see a lot of things like try catch, right? So the idea is whatever the program says it's returning, it might also crash. So there's one more possibility. You can think of this maybe X as being X plus 1. Yeah. And again, we have a similar unit map eta here, which given an instance of a type, in particular, that's an instance of the maybe type, right? It's just, it didn't fail. We also have a way to interpret maybe X as maybe X. And all we do is sort of collapse the two failure states, right? This thing on the left, it could fail in the first maybe, or it could fail in the second maybe. And either way, we treat that as a failure. So we have this, this structure map. And again, we can check that sort of exactly the same properties are satisfied. I mean, I won't talk through all of it, but somehow there's different ways of treating failure, and they're all equivalent to each other. But then what is a model? Oh, I guess I have a typo here. This should be maybe semantics. I wrote list. So what are the models for maybe? Does anybody know the algebras here? So interestingly, this example is a little different from the list one, because we actually get all, well, we get the same. Before we had lists as examples. Here we have maybe types as examples, but those are all the examples. We don't have any new ones. So every algebra for maybe is itself a maybe type, but you can say that in a slightly different way as they're pointed types. So they're types where one particular instance of that type is designated as null. Now, this is, of course, this is a very dangerous type of data structure to use. There was the story about the two married lawyers who got null and void as their license plates, and then the guy with null just kept getting parking tickets, like thousands of parking tickets every month for anyone where they didn't have the license plate in the database. So it's dangerous to have a null value as part of your type, and yet it's also very common. And it's especially common in neural networks where you often see tensors used as masks. So this is where you might have a tensor of zeros and ones, and 0 means no value, 1 means some value. There, the sort of notion of absent data or a crash or whatever is somehow implicit in the data structure itself, right? So any pointed type, a type with a designated null type, that's an algebra for maybe. I wanted to make one more observation about maybe computations. So if we have two arrows like this, X returns a maybe Y and Y returns a maybe Z, the observation is we can compose these arrows. It doesn't look like we can compose them because the endpoints don't match up, but we can compose them using this formula on the third line. So we do the first map, and then the second one gives us a map not from y into maybe z, but also from maybe y into maybe z. But then maybe z can be mapped, as we said, to a maybe z. So we can sort of chain through this structure map for maybe to compose computations like this. I mean, this is a complicated way of saying something obvious, which is run the first program. If it crashed, don't run the second program, right? But just spelling it out here, the fact that we have this map from maybe squared to maybe, it means that we can string these together. And these arrows mapping x to maybe y, these are called Kleisli arrows for maybe. And these are a pretty central topic of discussion, I think, in functional programming. And so I wanted to really single them out. Okay, so I think we're ready to define a monad if there's no further questions about the two examples of list and maybe. Okay, so a monad is a functor on a category. So from a category to itself, equipped with two natural transformations. One from the square, this means square under composition. Yeah. One from t squared to t, and then a natural transformation from the identity functor on C to T. And they must satisfy these commutative diagrams. And remember, these are basically homework. The thing on the left is what we should be thinking about. It's some way of collapsing t squared down to t, as well as expanding the identity into t. So it sort of is, it like really wants everything to be a t type. Not a t squared type, not a non-t type, but wants everything to be a t type. And then same story, an algebra for this monad is a particular object equipped with a particular way of unpacking, of un-t-ifying t of m, satisfying these diagrams. You know, again, don't worry in the first place about the one on the right. And now, if I have two T algebras, M and M prime, I want to say that these algebras form a category. I said this sort of implicitly with lists, but let me be explicit. The morphisms in this category, so a morphism of algebras is some arrow in our category, but it should satisfy this square. It should fit into this square so that doing phi and then doing the sort of unpacking should be the same as unpacking and then doing the phi. Yeah. Now, one thing to check is to check that I told you the right definition for monoids, right? So a morphism of monoids is normally defined to preserve the binary operation, etc. So I claim that if you do this for list algebras, you get the same definition. Okay, so in general, I want to say what a Kleisli arrow is. So it's these morphisms from x to t of y, and you compose them, as I said, which means that they form a category. So we have this in addition to the category we started with, and then the category of algebras. We also have the Kleisli category, but as an exercise, you can show that this is actually a subcategory of the category of algebras. So it's the subcategory of algebras that are of the form T of X. And that means that, you know, you can, I mean, I see a lot about the Kleisli category in, say, writing on functional programming, not as much about the Eilenberg-Moore category of algebras. But the point is the Kleisli category sits inside the category of algebras. It's the free algebras. So let me stop to see if there's any questions about this set of definitions, because that was kind of a lot before we go back into examples. Not seeing any. Right. So to go back to lists briefly, I want to say that there's a bunch of monads that all feel kind of similar to list, and I just wanted to run through them quickly. So we did lists, but then there's also bags, which are, you know, sort of like lists, but without an ordering. Finite subsets. So you look at like sort of all the binary classifiers on your type that only say yes to a finite number of things, and then the sort of all the subsets, all the binary classifiers. So let's go through these. We said that the algebras for list are monoids. Can anybody tell me what the algebras are for bags? So remember, a monoid is a machine for turning lists into, for smushing down lists, right? An algebra for lists is a machine for smushing down lists. What's a machine for smushing down bags, right? So it's kind of the same as lists. A bag is kind of like a list, except it doesn't have an ordering, right? So if you think of it like a list, it had better be true that you get the same answer regardless of what order you do it in. Commutative monoid is exactly right. Yeah, so commutative monoid is the same as an algebra for the bag, sometimes known as the multiset monad. Okay, now how about finite power sets? So now what I want is I want a machine that can take any subset of my set and sort of join them together to an element of the set. You can sort of join any finite number of things in the set together. What does that sound like? So the algebras for the finite power set monad are semi-lattices. They are sets with a join operation, satisfying kind of sensible lattice axioms. And then what do you think the algebras are for the entire power set functor, the one that lets you join anything at all? Well, they're complete semi-lattices, which turn out to be lattices. So as you can see, there's this whole family of, I'm calling them container monads, that are really about ways of collecting things and distilling them down somehow. And they each give a different notion of that. So here's some slightly more programming-oriented examples. So suppose I look at this functor, right A. So what does this do? It just multiplies any type by A. So in other words, it takes a type and it returns the type of pairs, one from X and the other from A. So the point is that a Kleisli arrow for this, it's really about like returning an extra thing of type A. But can we really make this into a monad? There's some condition that we're missing for this to actually be a monad. And that condition, I'm waiting to see if somebody says it. The condition is that A has to be a monoid. So in order to have, for example, just let X be the one element set, then this is saying that we need something to map from A times A to A, and we need something to map from 1 to A. So in fact, this functor is a monad, or has a sort of natural monad structure on it, exactly when A is a monoid. So this is actually a really funny thing, because going back, you know, this definition of a monad, you know, this is responsible for the pithy statement that a monad is just a monoid in endofunctors, because this is basically a definition of a monad, or of a monoid, excuse me. But here we actually see something funny. So you might say that monads are special cases of monoids, but here we find that monoids are special cases of monads. They're the writer monads. So I always found this quite interesting. And to me, this is a more natural way to think about it, is to think about monoids as monads rather than the other way around. And furthermore, the algebras for this monad are actually what we would normally call the modules for the monoid. Now, you may or may not have heard this term, but for example, if we put a group here, then the algebras are the sets with an action of the group. So in fact, this notion of a group action is a special case of the notion of a monad algebra, just for this particular writer monad. We also have the reader monad, and this one's a little better. It's always a monad, because if we have a reader that returns a reader, then we can use that as a reader by passing the same thing into the reader twice. And furthermore, any element of X will give us a constant reader, the reader which always returns that element of X regardless of its input. So hopefully it's clear why this is called the reader monad, but interestingly enough, in general, it's quite tricky, I think, to say what the algebras are. But when A equals 2, this is a kind of slightly hard, maybe, exercise to characterize what are the kind of semantics for reading from 2, right? But anyway, this is this reader and writer are kind of fundamental building blocks. Right. So a question about the technical definition. So about algebras and so on. So I'm being a little bit sloppy in my terminology. So this is the definition of an algebra for a monad, and I don't like the term very much. It's a standard term, but I think it's more useful to think of it as a module or as a model. So I'm accidentally saying those two things sometimes instead. To me, an algebra in this sense, it models the semantics. So the monad is sort of a structure, and then the algebras are its semantics. To the semantics, but anyway, but I've only really defined algebras, so just don't worry about these other terms. So as far as the semantics for A equals 2 versus A equals 3, well, I think I'm not sure if this is known. Let me put it that way. I'm not sure if the answer to this is known for A equals 3, but there is a reasonable characterization for A equals 2. Some of these ones, some of the ones that look the most relevant for programming are actually the hardest to work with, because often their algebras include massive classes of programs that might interact with data in this way. So like there's a lot of different ways to call a reader. So it may be characterizing the algebras becomes tricky. Okay, so here's one more definition, which is a comonad. I don't expect this to be a useful definition, but it is a functional one. So comonads are just monads where you do everything backwards. Now, this makes it look like the definitions are really symmetric, and they are. Comonads and monads, in a sense, they have all the same theory to them. But the issue is that since we're normally thinking of types as being something like sets, the category of sets is very different from the opposite of the category of sets. And so monads and comonads feel really different from each other. And one way to say it is monads are all about producing kind of more interesting results than you expected, and comonads are all about requiring more interesting inputs than you expected. So, you know, a monad, instead of returning a value, it returns a list. A comonad, it's like instead of taking a value, it takes like a view into a stream, right? And then it sort of selects its data out of the stream somehow. And I would say that it's a common bad habit to neglect comonads in favor of monads, and that's I'm doing that in this talk, but don't be like me. Comonads are really important, but there are 4 slightly different problems than monads usually. So I've found it to be really interesting. There's a lot of nice work going on these days with the use of comonads in like front-end design, UI design and stuff like that, because sort of it's all about laying stuff out and so on. So very often there's really interesting stuff to say with comonads, but again, I'm pretty focused on the monads in this talk. But keep an eye out. And then I wanted to make this observation, and also why I keep saying models for semantics. Well, if I have 2 adjoint functors, which I defined earlier, if I have 2 adjoint functors f and g, exercise, just unravel all the definitions I've said. There are 2 functors that I get by composing f and g. I can start in d and I can do g and then f. I can start in c and I can do f and then g. And the fact is that doing this, if f and g are adjoints, this always gives me a comonad on d and a monad on c. And this can be a nice way of quickly showing that a thing is a monad. Often there's a lot of natural adjunctions around, and this sort of gives you a free monad. Okay, so my question is, if every adjunction gives you a monad, and every monad gives you an adjunction, are monads and adjunctions the same? Well, no, but there is an adjunction between them. So there's an adjunction between the category of monads and the category of adjunctions, and it's called the structure semantics adjunction. So I'm emphasizing the fact monads, somehow the word to assign to monads is structure, and the words to assign to their algebras is semantics. So remember, the algebras sort of sit over set in this in an adjunction, and in fact, both the Kleisli category and the Eilenberg-Moore category, they both sort of live in an adjunction over the original category. But somehow the Kleisli category, I mean, I won't say what this means exactly, but somehow the Kleisli category isn't complete. This category of algebras is complete. It's sort of you're done. The Kleisli category somehow wants to be expanded to cover these other examples. So when you have a choice between working between the two, I would say you should, I mean, this is my strong bias as a mathematician. You should prefer to work in the category of all the algebras, not in the Kleisli category. However, in some situations, it's very hard to describe and to work with the entire category of algebras, whereas the Kleisli category is always nice. It's always easy to describe the Kleisli category. So in situations where you can't say what the algebras are very easily, then maybe that's a good excuse to stay in the Kleisli category. So Callie asks, what are the monads associated with the common kind of free and forgetful adjunctions? So, I mean, in a sense, the answer to that is all monads, because every monad gives you such a free forgetful adjunction. As far as common types, there are various conditions you can place on monads, like probably finitary, a lot of them, or I'm not sure. But this adjunction on the right here, this is somehow an essential free forgetful adjunction. This T is sending elements to the free algebra on, or sorry, sending objects to the free algebra on that object. And this U is a forgetful functor. So using this fact, let's actually make a monad. So you may remember exponential objects from Peter's talk. Now, it's not how he described them, but you can describe the exponential as a right adjoint to the product. So in other words, maps out of the product are the same as maps into the exponential, right? And this is also known as currying and uncurrying. So we've got an adjunction. That means we've got both a monad and a comonad. So what are they? They are known as state and store. They formalize stateful computation and, let's say, retrieval from storage, or like updating storage. And you can sort of, doing some curry and uncurry yoga, you can see where they get their names. So first of all, a Kleisli arrow for state means a map from X into state A of Y. Such an arrow, you can, I always mix up currying and uncurrying. I think this is uncurrying. Uncurry into such a map. So a map from X into state A of Y is the same as a map from X times A to Y times A, which, if you think about it, a map from X times A to Y times A is exactly a stateful computation that takes an X and returns a Y, but in such a way that it depends on and updates some state A, right? And then for the co-Kleisli arrow, I didn't really say what that is, but you just reverse all the arrows. We can do something similar and find that a map out of store A of X is the same as a map between sort of functions from A to X into functions from A to Y. So in other words, A is sort of like the keys for a lookup, right? So this is saying my input isn't an X, but it's a sort of dictionary with A as its set of keys and X as its values, right? And then it returns something with A as its set of keys and Y as its set of values. So so it's like a map over a dict. Now I don't know very much about these, so I think it's not incredibly easy to describe the algebras for state, but maybe somebody else here knows better. Maybe Bruno will tell me later that there's a paper about this. But the co-algebras for store are lenses, which you may not know lenses, but they're being used quite a lot these days. They sort of model getter and setter logic. Like that's really the thing of interest in lenses is and these things have been used, for example, to model gradient descent in neural nets, because the whole point of a neural net, you have a forwards pass and you have a backwards pass, and you can sort of, well, Bruno's, I would say see Bruno's talk to get a sense of these things, you know, sort of, imagine like putting something in the forward pass, getting it in the back. Anyway, so again, these are important monads for computation. So okay, question is there a relationship between monads and Levier theories? Yes. Levier theories, if I have this correctly, Levier theories are in some sense equivalent to finitary monads. So a finitary monad is a monad that's sort of determined in a natural way by what it does to finite sets. So not many of the monads I've mentioned are finitary. So like the finite power set monad is finitary, the power set monad is not, the list monad is finitary, the bag monad is finitary. So basically Levier theories are situations where you have a monad that's described by a finite theory, and it's a way of packing that thing up into a category. It's not so easy to say a lot beyond that, but there's a really nice paper by Eugenia Cheng about distributive laws between Levier theories that goes into a lot of detail about the correspondence between the two. So I would sort of generally gesture in the direction of operads and so on as saying there's a lot of interesting connections there. So in fact, I would add some of what I'm saying about monads is this is sort of stuff that we found useful, Petar and I, in our paper. But some of what we did, we now know is more natural to express using Levier theories. So there's a lot to say. There's a lot to say there. It turns out that we accidentally described the Levier theory for commutative semirings while also describing the monad for commutative semirings. So I hope that helps. So let's see. Moving on to more examples, and feel free to ask more questions. I may be going a little fast, so there may be plenty of time for questions. So feel free. As far as not being able to characterize the algebras for monads, we have the continuation monad, and this is a really interesting and kind of essential one, because what it's really saying is saying, having a program that doesn't, instead of returning, what's the right way to say it? It's like, instead of returning a y, I return something that takes programs turning y's into a's and then secretly does something to them to end up with an a. This is not my area of expertise, but I think that you can write quite a lot, maybe any program, using this kind of style of continuation passing. And so in principle, the algebras for this monad describe, possibly even all of computing. I'm not sure about that, but there's definitely a lot of ways of calling functions. And a lot of those are wrapped up in being an algebra for this monad. One of the interesting things about this monad is it's actually the square of another functor. And this functor, you might ask whether this functor is a monad. Can anybody tell me why it's definitely not a monad? Why can this functor definitely, this one on the right, why can it definitely not possibly ever be a monad? What does this functor do to arrows? If I have a map from x to x prime, what happens to that arrow? So I get a map sort of in the wrong way, right? If I have a map x to x prime, I get a map from x prime a into xa, right? By precomposition. So unlike the reader functor, this one, the arguments are switched. Yeah, the reader functor is fine, but this is actually not a functor, or rather it's a functor from set to set op. Yeah, it reverses the direction of arrows. So the way we've defined monads, that can't possibly be a monad because it's not a functor the way we described it. But it's a very interesting functor. But you have to do it twice to get the arrows to switch back. That's kind of the tricky thing. And this is what leads to the notion of a continuation. And this, for some reason, this monad comes up absolutely everywhere, not just in computing. So a nice example here is in the category of vector spaces. If A is, so say category of vector spaces over the real numbers, if A is the real numbers, then x bracket R, x bracket A is just the dual vector space of X. So this continuation is then computing the double dual. But there's more, because in logical systems, like if I have a sort of lattice of truth values, then I would often model the negation of X as being X implies false. So the ham from X to false. So then the double dual is basically when you let A be false in a suitable category, or the double negation. So this continuation monad, it seems to be very specific to programming, and yet somehow it's, it's related to vector spaces. It's related to the law of the excluded middle, because the law of the excluded middle says that this map, it says that the unit of the continuation monad for false is an isomorphism. So if you that's an interesting thing to look into. Can you extend this to logic without the law of contradiction? So yes, 100% yes. So I don't have any remarks prepared on this, but one of the things that I did my thesis work in is so-called pointless topology, which is sort of like an intuitionistic logic version of topology, where you can even have spaces that don't have any points on them, and so on. And this double negation comes up there, and it's very interesting. Sort of like if you take the real numbers and you kind of look at the part that's preserved under double negation, you end up throwing out all the points, but you still have the topology of the reals, just with no points. If you're curious about that example, I think it's called the pointless reals. So anyway, there's a lot of this particular monad comes up a lot in intuitionistic logic, which is basically logic where all the normal rules hold except the law of the excluded middle. That one, you have some flexibility. And yeah, this actually, well, one more comment on that is, sometimes people feel that, I think maybe computer scientists are the least like this, but sometimes people feel that removing the law of the excluded middle is fanciful. But if you even take the real numbers and take the open sets of the real numbers, already that's a system that sort of follows the rules of logic, but not the law of the excluded middle, because then the negation of an open set isn't the complement, because that's not necessarily an open set, but it's the interior of the complement. And so then you can check that if I do that twice, I don't necessarily get the same thing back that I started with. So this is sort of a very natural thing to look at, even for sort of topological spaces. Okay, so I have one more example I wanted to slip in before talking about distributive laws. So this definition might be a little hard to read. It's easier to say it in words. So these are T of S here. This is the finite probability measures on a set S. So by finite, I mean for all but finitely many elements of S, this should return 0. And then whatever it returns on the remaining ones should be real numbers, positive real numbers summing to 1. Yeah. So finitely supported probability measures on S. This is just to avoid having to talk about like how we integrate and so on. So this is a monad, which is a fun exercise because you have to think, well, how does an element give you a measure? And then how does a sort of measure of measures give you a measure? But this kind of monad, I mean, there's many things that have this flavor, but this kind of thing really seems very interesting to study in probability and statistics. In fact, this monad, it comes up in neural nets. I mean, if you look carefully at how sort of original style transformers are constructed using softmax, it's really related to this monad because they're really you really kind of produce a probability distribution over positions. Yeah, that's a kind of important step in doing this computation in transformers. And it's interesting. The algebras are describable as convex spaces, and very roughly that sort of means, you know, any set where you have a notion of interpolation between points. So in particular, any convex shape, any sort of convex polyhedron will give you an algebra for this monad, because if you have sort of probability, like if you have, what's the right way to say it? It's if I weight the points in something convex and compute the weighted average, then convexity exactly means I stay in the shape, right? So so I think this is a really interesting one to think about. I think it's implicit in a lot of machine learning work, including policy gradient and so on. So it's worth mentioning, but this is far from the only kind of connection that monads and probability have. Okay, so can you prove convergence theorems using ideas like this? I'm not sure that I can, but I believe that somebody can. I think a lot of times you have some convergence theorem which maybe you have this convergence theorem over here and this convergence theorem over here and this convergence theorem over here, and they all have the same proof, and yet they're not clearly, you can't clearly turn that into a single proof that covers them all. In those situations, I think a lot of the times thinking about functors and monads can be really powerful in making a proof. So if you wanted to prove a convergence theorem, but also prove 7 other convergence theorems at the same time, you probably can do this, and probably there are some papers taking this sort of synthetic approach. Question is, what category is this monad defined on? This is just defined on the category of sets. So that's why, I mean, if you do this on finite sets, you don't need to have this annoying condition, but I just sort of said finitely supported, yeah, to make sure that we don't run into any trouble. But yeah, there's no problem defining this on all sets. It's kind of a similar issue as with like the finite power set monad. Like it's shouldn't be any problem. Because yeah, I mean, we're starting with a set and we're returning a set of probability distributions. It's sort of the extra structure to it that gets interesting. Okay, So now I'm going to talk a bit about what Petra and I did in our paper, which, I mean, not that the paper is that interesting, but I think it's good to know about distributive laws. So the basic problem is, what if I have two monads and I really care a lot about both of them and need to do something interesting with both of them? This is often overlooked, but I think, you know, like people who code in Haskell, I think have heard the term monad transformers. So the point is that you can't just stick two monads together. There are problems. And the sort of most obvious way to state this problem is that the composition of two monads is generally not a monad, or there's no natural way to make it into a monad. But in some nice situations, you can do this. There are no-go theorems here. I think it's often the case that you have two really interesting monads and you would really like to use them both at once, and there might actually be a theorem saying that no such thing exists. So I think that's the one challenge of working with monads, is you often need to very carefully sort of build up the structures that you want to use, and you may find that they exclude interaction with other structures. I think these problems exist even if you don't use monads, but I think monads make them really obvious how hard it is to kind of get everything to type check. So, so what is a distributive law? Well, first of all, here's a figure from our paper, and if you squint a little bit, you can see that we're sort of factoring a computation through Kleisli arrows, namely Kleisli arrows for list and for bag. Now, for this to work, we need our R here. We need it to be an algebra for list, and we need it to be an algebra for bag, and we need those structures to be nicely compatible somehow. This is possible, but it's only possible because it turns out that bag composed with list, that is list and then bag, turns out that's a monad. But this is delicate because it's false the other way, right? List of bag is not a monad, but bag of list is a monad, or we can make it a monad. Being a monad is not a thing you either are or aren't. It's a structure that is assigned to you. So here's what a distributive law looks like. And I won't go into tremendous detail here, but it's some lambda that kind of distributes lists over bags. So it takes a list of bags and it maps it to a bag of lists. And then it should have this sort of compatibility condition at the bottom, which sort of says, well, something sensible about different ways that you might distribute a list of bag of bags, right? And given such a thing, which it turns out is the same as a monad in the category of monads, given such a thing, you can define the algebras for bag of list. So does anybody, can anybody tell me what is an algebra for bag of list? So in other words, another way of saying it is, what do we call something that's both a monoid and a commutative monoid in different ways, but where they're compatible with each other? So ring of some kind is pretty good. Semi-ring is exactly right. So some people call them rigs. It's a little bit more than just bags. You can get lists that distribute over sort of formal sums. So in other words, like you can do monoids and abelian groups, and then you get rings exactly. But in this case, we don't have negatives, so it's just semi-rings or rigs. And in a sense, this whole thing was just trying to justify the use of semi-rings. It was trying to explain why those seemed to be really important. Like there were a number of papers talking about semi-rings and so on. So we wanted to like really explain why semi-rings in particular were relevant for this kind of computation. So we're just about at the end, actually. I've been going pretty quickly, so maybe we can sort of hop back for questions. But thank you, everybody. This is the last lesson, but we still have more planned. There are some guest lectures that I think could be really exciting. We're going to send out a sort of resource about here are some next steps, because we don't want people to kind of stop here. But this is also, it's a really open area at the moment. I mean, there's a lot to say about category theory and programming, but the applications to deep learning are very new, and it's been really great to be able to bring this sort of emerging field to all of you. And thank you so much for bearing with us this time. And happy to take further questions or.
Can I start with 2 questions?
Yeah, please.
Okay, so regarding the category of algebras, can you explain a little bit in some examples, kind of the relationship with the Kleisli category? So like what algebra do we get from like, so maybe let's take a probability monad. Can you, like the Kleisli maps as stochastic maps, or the algebras that are associated to that?
That's a good question. So, I mean, I can say my own thoughts in a second, but it's a good question. What is the Kleisli category for this? And this is just, this should be like simplexes. So like, so for example, like on finite sets, so again, the Kleisli category, this is like the free algebras. Okay, so that's kind of the general philosophy here. It is sort of, you have the category of all the algebras, and then the ones that are free, that sort of have no relations in them, that's the Kleisli category. So,
does that always exist? So for any monad, there always is a free algebra. Is that a general thing?
Yeah. So at S, like you start with S, T of S is the free algebra, or at least I should say, you can, there's a natural way in these Kleisli arrows, you can equip T of S with the structure of an algebra. Yeah, it's just, I mean, in the sort of sensible way, namely T of S maps to T of S using the monad law. So for any S, T of S is an algebra, and we call that.
So what is the map? What is the map T of S to S then?
Well, it's a map T of S to T of S.
Yeah, of course. Yes.
Yeah.
Okay.
So we just call that the free algebra on S. Yeah.
Okay.
So then, I mean, some monads, all the algebras are free, like vector spaces or the maybe monad. You have all the algebras are free, but then sometimes there are non-free algebras. And I think in this case, I would have to think a bit about like how interesting convex spaces can be. But like I think like if you apply this to like a 3-element set, say. You get the set of A, B, C with A plus B plus C equals 1, all between 0 and 1. So you get like a filled triangle, right? Every free finite algebra is going to be a simplex like that. And then the question is, can we come up with an interesting convex space that's not isomorphic to one of those? I'd have to I'd have to think a little bit. Probably yes, but I don't know off the top of my head.
Can I ask one more follow-up question?
Sure.
So you said that the Kleisli category is a subcategory of algebra. So could you give an example of, for example, for the probability monad morphism of simply says that, like algebra morphism of simply says that is not a stochastic, that doesn't correspond to a stochastic map? Would it be? Towards asked, or for another monad. I'm just curious, like, what is the sub? Like, how is it a subcategory?
Well, I mean, I didn't say full subcategory because then I would have had to define what full meant. But it is a full subcategory. You get all the algebra morphisms between the free algebras. So there's, in order to say something interesting, you would have to have an interesting algebra.
Okay.
But I was going to add one more thing about this, which is, I guess I don't know how helpful it is for people who aren't me, but like one of the core examples I always come back to is rings, because the sort of ring theory in like the late 1800s basically meant polynomials, basically meant the theory of polynomial algebras. And it was the abstract definition of a ring that sort of saved the theory. Like it was sort of all the proofs were horrible and so on. But then as a result of having an abstract definition of a ring, suddenly you had things like the Noetherian property and so on, where things could be proved with a sort of abstract nonsense kind of way, but it became very elegant and so on. And this was exactly an issue of the Kleisli category, because the functor in question sends a set to the polynomial ring generated by that set, or with indeterminates drawn from that set. And so that's a monad. And its Kleisli category is just the category of all the polynomial rings. But then its full category of algebras now includes all commutative rings. So this is, to me, that's sort of the essential example of how it is that a Kleisli category is completed to become the category of algebras. Because, for example, polynomial rings, they're not closed under quotients, right? So if I have a map of polynomial rings, the kernel isn't polynomial and so on. But now we move into this general commutative ring. Anyway, so let me actually get to the questions here. So whoops. Oh, okay. Sorry, I accidentally answered. If you're talking about semi-rings when describing the algebra, do other algebra concepts mean anything? Say ideals. Ideals, I would, think of them as kernels. To get into well, there's a lot I can say here, but maybe nothing really really simple. But I would say that, like, you're going to have a much easier time making sense of ideals in the algebras, category of algebras, than the Kleisli category. But yeah, that's the place sort of to think about those things, is, I guess, my quick answer. Sorry, I'm struggling a bit with the question tool, because on the web interface it sort of moves the questions around while you're clicking at them and so on. Somebody asked to go over the first slide. Somebody they said they had a stupid question about this slide. What, Pim? Can you manage the questions? They're just like
yes. I think that Dobrik is referring to the first slide with these kind of rectangle. Oh, sorry. Dobrik asks, thanks. Why is the first set of arrows inverted? We
Okay,
see,
yeah.
I guess, the arrows going up there.
Hopefully that's not because I made a mistake. So this bracket is covariant in the second argument, but it's contravariant in the first argument. So if I have a map from y to y prime, then as on the right, it gives me a map. I take a function up there and then I just compose it afterwards with the function from y to y prime. But if I do that on the left, the arrow goes the opposite way now because I have to pre-compose, if I have this right. Yeah. Now I have x maps into x prime, maps into y, right? It sort of operates on the other side. I don't know if that helped, but.
It's a question by Matthew, and maybe you can go back to kind of the basic definition. The question is, could you go over the intuition between the relationship of a monad and their algebras? So maybe just kind of recap the definition of an algebra.
Sure. Yeah. Well, so to recap, again, it's sort of a way of unwrapping the monad somehow. So the relationship between monads and their algebras, I guess, like a lot of people think of monads in terms of the Kleisli arrows. So, that is to say the monad T is really like what it's really describing is computations that look like this, computations that take X's and don't quite return Y's, but they return some like modified version of y. So, for the computations that you might hope return a number, but actually they return a list, something like that. And so this Kleisli category, the objects are the objects of C. That's sort of the critical point about the Kleisli category. Same objects, different arrows, but same objects. So in this way, you can think of the monad as being sort of a different structure on the category itself, like a different notion of enhanced arrow on the category itself. And then what's the relationship between that and the algebras? It's a little bit subtle, but like the main point is that there are things that act as if they're in the Kleisli category, but they're not. And as this is why I started with list, which is like I've had programmers kind of tell me that the notion of monoid is so ridiculously abstract that it's sort of nonsense to even talk about. But then everybody writes, list comprehension code that uses monoids, right? So that's why I started with lists, where anytime you're doing a fold over a list, right, you're using something that's not obviously part of the monad, right? You're using something like a Boolean and aggregating into it, or an integer aggregating into it, right? So this thing that you aggregate into when you fold over a list, like that's the algebra. It's not directly related to lists, but it's somehow implied by the notion. I don't know if that helps at all, but.
Thanks. If Matthew has a follow-up question, maybe you can ask in the Q&A. So next question by Ed Wieke. Monads seem like abstractions of a general, of familiar general algorithms like dynamic programming, primal dual optimization, expectation maximization, etc. I guess the question is, do you agree with that?
Yes. I can't manage to scroll to the question. So do I agree with monads Sorry, what am I
being
agreeing?
abstractions of familiar general algorithms. Or
Mm.
can you say something about the relationship of how monads may implement or
Yeah.
encode
Well,
algorithms?
so in a sense, the thing that I'm thinking about most of the time these days is what really is an algorithm? Like, what's the right definition for a general algorithm? And I don't know, which is why I keep thinking about it. But I definitely think that the monad view is a nice direction to come at this way of thinking, and it does seem to cover a lot of examples. I mean, we thought this way, we were trying to describe something that could be expanded to describe, lots and lots of dynamic programming algorithms, not just a few. So I do agree that there is something quite general here, but it's a little hard to say what it is. I would say that the sort of de Moore's thesis kind of poses that general dynamic programming is about somehow expansion, scoring, and recombining. And this to me feels very much like describing this. You want to talk about distributive laws between monads or something like this. Like, it seems highly relevant. So I mean, in short, I agree, but I'm not super confident on the specifics.
Right. And let's pick next question. A question by Tali. Okay, so monads are monoids in the category of endofunctors. Now, just as a kind of floaty analogy, can we see monoids the same as arrow composition in a one object category? One wonders, can you add objects to the whole monad story? What happens? How can this be made concrete? So I guess the question here is that, so monoids, so monads are monoids, and monoids are one object category. What happens if we add multiple objects if we replace the monoid in the definition? So I guess then what is a category in the category of endofunctors? I think is the question Tali is asking.
I think if I try to give too specific an answer to this, I'll probably confuse myself. But I think the part of what I was getting at in this slide is you can define both a monoid and a monad in basically the same way, which is that I take the category that's just one object and one arrow, and then I look at the ways of mapping that into another category. And if I do this correctly, I should get either, well, let me, if I do this laxly, actually, how do I get monoids this way? Anyway, you can definitely get monads this way. So like somehow the point is that you think of a monad as being sort of an arrow attached to an object, the object being the entire category. So you kind of work in the two category of all categories, and then you have this now completely internal structure, and you can say an object is a monad and so on. But yeah, I don't know. This is at the limits of what I can confidently speak about.
Okay, there is a follow-up question by Matthew, who previously asked about the algebras. He asked, so the reason you want your algebra to be commutative over the bag monad is because you can't guarantee order. Maybe you could elaborate or sort of make that clear?
Yeah. Well, so I guess this is, all these things can be worked out from the definitions, but like a rough a rough way to say it is that the bag monad sort of is the list monad, but where you've identified lists if they're equal up to reordering. Yeah. So by this reasoning, an algebra for the bag monad should be able to handle the list monad somehow. It should do fine with lists, but it has to treat them uniformly. It won't be able to tell the difference between if you reorder the list. I mean, that's a sort of, you know, ad hoc argument, but that's basically what's happening. You know, you define the operation by looking at the join of a two-element bag, right? But yeah, I'd have to think about exactly how you get commutativity out of that. But if you look at the two different injections of one element into a two-element bag, then you can probably conclude from the axioms that you get a commutative operation.
Great. Can I ask a very practical question of myself on the graph nets? Could you go to the slide where you had all the monads there regarding the
graph net,
the span, the graph net?
This
yeah.
bit?
Yes. So I'm wondering here, what does the list do? So Y, I guess, is a set of edges. So what is the list of R?
Yeah. Well, so this is in a sense, this picture is more general than it needs to be. First of all, the examples that we're working with, usually the list only has two elements, and also the result doesn't depend on the order. So this could have been the bag monad, but it would have made the paper even more confusing than it already was to have a there is a distributive law of the bag monad over itself, and it was just, anyway, so we did it slightly more generally than we needed to with lists. And the idea, like this part on the top, like this was sort of this was the part we struggled with the most, and is why we started thinking about polynomial functors and so on, rather than just, like, we use these polynomial diagrams rather than spans, because we needed this top arrow to explain some very mysterious things that were happening. Namely, you know, supposedly nodes were sending messages, and then nodes were aggregating the messages that they received. But then also nodes were allowed to somehow, like, mediate the messages they were being sent at the source, which meant that somehow they were also sending, you know, like, it was more like the sender and receiver were cooperating to send a message to the receiver. Yeah. So that's kind of what's happening in this top arrow, is that's where the sender and the receiver, or you could even do two senders, they interact with a sort of multiplicative connection. And then the aggregation of messages occurs with an additive connection. So it was sort of important handling those things differently.
So can you, in like, if you think of like this being a pair of data from the start and the source and target of the edge, can you model like any like neural network layer that takes these two as an input as the multiplication in your rig?
That's a little bit of an open question. I mean, and probably there's some things you can do that don't feel very multiplicative. I mean, but I don't know. Yeah, philosophically, like, you could think of this as like concat and then run it through a network. But then you get into questions of alignment and so on. But yeah, I mean, in principle, this sort of pattern of like concat then aggregate or something like that, like, is sort of common, I think.
Okay. So maybe as a final question, a very difficult one, Situ asks, I know you said it's a new subject, but I'm wondering if you could speculate about where you see that this subject is going in terms of both the development of the pure math and in terms of a practicality, meaning can we improve neural network algorithms? And for example, Situ is very interested in whether we can learn categories and functors. It's a question also Bruno touched on in his talk, or refused to answer in his talk.
Yeah. It's a tough one. I mean, I think I'm always happy to speculate. I'm a chronic speculator, but you know, I have my very particular views on this. I mean, there's a lot of different directions where things are developing. One of the things that I'm really interested in is kind of working out how to kind of do, like, there's a lot of classical tools in, say, representation theory with a tremendous amount of explanatory power in them. And I think being able to apply some of those in what is necessarily a much more abstract setting of neural nets, I think this could be a quite strong thing. I mean, so anyway, like I would like to see the theory advance to the point where we can say a little bit more kind of a priori about what a network should or shouldn't be able to do. Like, we should have much better educated guesses about whether this thing will be good at this task, instead of having to, you know, spend millions of dollars running experiments every single time we want to know. So I think that's sort of where I'm focused, but I think a lot of the theoretical side, there's a lot to explain. There's a lot to account for, and I don't know. Probably about all I'm prepared to say. But I think, you know, being able to sort of do to, like, say, you know, we've got some representation, let's decompose it, figure things. Even, you know, I've been seeing, you know, some things done with, like, computer proof stuff in like Agda or something, where you run a function and it gives you the answer, but it also gives you a kind of proof that the answer is correct, right? So, like, wouldn't it be great to have a neural network library kind of built from first principles on kind of foundational ideas, where, you know, you plug in an abstract tensor, you get an abstract tensor back, but then you also get an object that encodes everything that's guaranteed about the relationship between the input and the output tensors, right? Sort of all the conservation laws are part of the output. So that's what I'd like to see. Maybe we'll get there.
Yeah, sign me up to that. Okay, maybe we'll leave it at that. There will be an email in the near future about when next lectures will take place. So keep an eye on that. Thanks, everyone. Thanks, Andrew.
Thanks, Pim.